Thanks everybody for being here today. And thanks for joining us for the second seminar, Global Change Seminar of the year. Today we have two speakers that will be talking about how we study biodiversity distribution and how global change is affecting that distribution and how we do conservation and management decisions taking into account that uncertainty. Each speaker will have 25 minutes to present, and we will have 10 minutes for questions at the end, so save a few questions for the end of the talk. Our first speaker, joining from Brazil, is Dr. Clinton Jenkins. He got his PhD at the University of Tennessee at the Department of Ecology and Evolutionary Biology. Then he worked as a researcher at Duke University, University of Maryland, here at NC State. And in 2013, he started as a professor at the Ecological Research Institute in Brazil. He has conducted several studies about distribution of species, endangered species, and conservation of endangered species. You should definitely check his website. He has amazing maps, global maps of biodiversity distribution. Our second speaker is Krishna Pacifica. He's an assistant professor in Fisheries, Wildlife, and Conservation Biology in the Department of Forestry and Environmental Resources here at NC State. And he is also a faculty fellow in the Center for Geospatial Analytics. He has 2 master's degrees, one in wildlife ecology from NC State and one in statistics from the University of Georgia. And he got his PhD in forest resources from the University of Georgia. So, Clinton, can you hear us well?
Yes, I hear you well.
Okay, so you can start your talk whenever you want.
Okay, all right. Well, thanks for inviting me. Hope this goes well. I'm sort of connected here from rural São Paulo state, but usually the internet is pretty good here. So what I'm going to do is give sort of a global overview of biodiversity and some of the work I've been doing on priority areas for biodiversity conservation actions. First, just a really brief summary of who I am and what I do. You've already got some background there. I've been at this for around 20 years since my graduate work, part of which was in Brazil. And I've lived in Brazil for the last 6 years since I moved from Raleigh actually to here. But so I have a sort of a split life between Brazil and the US. And I do a lot of this sort of cross-disciplinary research and conservation. You know, a lot of it's biodiversity focused, but most of conservation is really dealing with people and trying to get places protected. And sometimes the biological part is the easier part, but we'll focus a bit on the biology here though. And I do what I term actionable conservation science, right? The kind of science that I think can affect real world decisions. And I hope you'll see a little bit of this. And this is actually a picture of my backyard, right? So it's quite nice to have tropical forest in your backyard. Endangered monkeys visit most days. So if we take a global view of biodiversity, we can perceive certain patterns. So this map here, this is a synthesis of range maps of birds, mammals, and amphibians, right? So these are sort of maps that you find in a field guide. They're digital versions these days. Give you a broad idea of where a species occurs. And so this is about 20,000 species, data from BirdLife, IUCN. And you'll see some pretty familiar patterns, right? The red and yellow areas are places with lots of species. I don't know, can you see the pointer when I'm pointing on the map?
Yes.
Let me see, I think I can get a bigger one here. Let's see. There's a laser pointer. Oh, this is better. So the red and yellow areas appear to have lots of species. The blue areas have fewer species, right? So deserts don't have much. The high latitudes, not so much. But this is only one way of looking at diversity. Granted, it's also a very small number of species for all of biodiversity, but these are the groups we have some decent data about. There's specific components of this we could separate it into, right? So as I mentioned, it's birds, mammals, and amphibians went into this analysis. And if you look at them as individual groups, the patterns are similar, but you start to see some differences. All right, so again, blue throughout all these maps, you'll see pretty much blue is fewer species and red is a higher number of species. So if you've got birds, and this is a little bird from the Colombian Andes. You'll see the Amazon here is pretty red. The Atlantic forest, I live right down here in the corner of Brazil. Parts of Central America, kind of yellowish, and then it's blue further up in North America. You know, if we look at mammals, patterns really similar. Amazon's got a lot, Atlantic forest quite a bit, similar pattern in Central America. Okay, well, we'll see this little monkey here again later. Okay. And then if you look at frogs, or really amphibians, most of whom are frogs of some sort, you know, the pattern starts to diverge a bit. You know, the western Amazon gets, you know, the red areas. The rest of the Amazon's kind of yellow and green. And then here in southeast Brazil, it's really red because there's all kinds of crazy amphibian diversity, lots of endemics. There's also lots of researchers there, so there's a little bit of sampling bias. There's more people looking for the frogs. And then the central parts of Brazil and South America, the deserts, they don't have so many amphibians. Right? It's a lower diversity. These sorts of things apply to the rest of the world. I'm just using South America because I have a lot of examples from there. But you know, richness patterns sort of co-occur for most groups of vertebrates across the world. If you're looking at broad patterns, but we can look at this in a different way, right? It's because not all of these species are equally. Let's say we don't worry about them equally for conservation. So let's look at the birds, right? Here's a zoomed in map of bird richness, species richness, right? So they have, you know, Amazon here cutting across South America, right? And down here, Rio de Janeiro. So if we take this, we look at it and say, well, this is the number of species, but I'm not interested in all those species because some of them are pretty common, you know, they're never going to go away, they're everywhere. And some are really rare, some are, you know, endangered. So what happens if we look at those species? Well, this map, this one has half of all the birds. So these are the half of the birds that have small ranges, right? So smaller than the median. And when you can consider those sort of more vulnerable to going extinct. Just imagine if you're a bird or some other species and your distribution is really small, it's really easy to lose all your habitat. You can have a disaster or a disease. It's easier to be pushed over the edge and go extinct. Right? So we probably worry about these species a bit more than something like, you know, European starling that's everywhere and really widespread. And these kind of species, they're really, really concentrated, right? So the Andes has a lot, Central America has some of the lighter blues and yellows and greens, Caribbean islands. Again, the Atlantic forest here is kind of a brighter blue. And then most of the planet's dark blue, right? A lot of that's actually zero, right? It doesn't have any of these species. They just don't. They're very concentrated geographically. So that brings an opportunity. It's like, well, you know, you can actually do conservation of lots of species in a fairly small area. But what about the ones, you know, we already know they're close to extinction? No. Oh, wait. Oh, I forgot this too. To better understand these sort of patterns of small range species, why are there so many in the Andes? This is, you know, the Andean mountain chains going up into Colombia. Here's Ecuador, north and Central America. If you look out over the Amazon here, you can sort of see on the distance the tepuis, right? And so this yellow and red band here, especially in the eastern Andes, has all kinds of endemic species. So lots of things really rare, only occur there. And topography tends to do that. So that's one component of biodiversity we could look at. But we've got evaluations for lots of individual species too. We have the IUCN Red List is probably the most known globally, where experts to get together and evaluate species one by one, decide based on some criteria if they're threatened or not, right? And how threatened, you know, are they at risk of going extinct? in the US, it tends to be based on the Endangered Species Act, whether a species is officially endangered or not. A similar sort of idea. And if you look at these species, well, the pattern starts to look a little different. The Andes here, that had all the small range things, there's still a lot of patches of yellows and reds and greens, right? So you got some endangered species there. But the Atlantic forest here, which is broadly these yellow and red and green areas of Brazil, it really pops out as having all kinds of threatened birds in this case. And this sort of pattern shows up for the mammals and amphibians too. Like, well, these are the things we know are really close to extinct. So maybe these are the areas we should focus on if we're worried about, the world changing and risk to biodiversity. And there are reasons that this occurs. So if you take a view of Brazil, on the left, we have is the original forest cover of the two big forests of Brazil, right? So the Amazon, right? Everybody knows the Amazon. Everybody talks about the Amazon. It's super famous, right? It's really big. About 4 or 5 million square kilometers of it's in Brazil. There's in some of the neighboring countries. And then you have the Atlantic forest, which is less known, but also originally was very large, right? Million and a half square kilometers, which goes along the coast of Brazil down to Argentina, a little bit into Paraguay. But if you look at it today, most of the Amazon, this green is still there, right? The Amazon gets a lot of news lately. You've probably seen, there are a lot of fires in the Amazon, some deforestation, which is bad. There's a lot of deforestation. But, most of it's still there. 60, 70% still there, which is pretty high for most tropical forests. Whereas you look at the Atlantic forest, and it's kind of had the crap beat out of it. Right? There's all these the good bits are these green bits, and then there's a lot of edgy forest, which is this yellow and orange is forest that's close to an edge. So if you combine this sort of map with, that earlier map of where you have these small range species, that's what generates all those threatened species. Right? Species were pretty rare to start with, or vulnerable, and then humanity came and beat the crap out of their homes and cut it down all the trees, and so you get lots of these species close to going extinct. Right? So broadly, if you can think of biodiversity in this sense, if you look at all the species together, you get this map here on the left, and it gets some interesting patterns. Tropics have lots of species, broad global patterns. And if you separate those out by groups, birds, mammals, amphibians, or other groups, if you have data, you start to get some more subtleties. But the really big differences come when you look at the distribution within the groups. Where are the rare species, the really restricted ones, and the ones that we already know are threatened. And those pull out particular areas of the world that are really the front line of the extinction crisis. Right? Those are the kind of areas I like to work. Right? That's what brought me to Brazil. Now, I want to give a sort of case study here on Rio de Janeiro. This place I've been working with people for about 20 years, ever since my PhD, and I'm giving it as a case because it's an example that's applicable in many parts of the world. Those concepts of how a species got threatened and what we do to try and improve its chances. It could be here, it could be in the US, it could be in Africa. It's very similar situation in many parts of the world. So going back to that map of threatened birds, right? There's a map very similar to this, my PhD, which brought me to Brazil the first time, in 1999. You see, the red areas here, the peak of it's really the state of Rio de Janeiro. And if you look at Rio de Janeiro, it's a state that has more than 700 species of bird have been recorded. So that's similar to basically the eastern US, if you put it all together. But it's packed into a really, really small area. Right, so Rio is about 45,000 square kilometers, and that's about the size of North Carolina, more or less. Right, it's about 20% forested. Depends on who's counting the trees and who's mapping it, and about 15% of the state's in some sort of protected area. Oh. Still connected? Okay, sorry. Power blinked here. So, you know, Rio de Janeiro, but if you think about conservation planning, you know, we don't protect a state. Right? You can't imagine, you know, that somebody's going to come in and say, hey, you know, North Carolina is super important for bird conservation. Let's protect North Carolina. Right? Nobody protects a place like that big. And Rio is the same thing. There's like 15 million people in Rio. It's a big part of the Brazilian economy, cities, agriculture. So we face this question of, well, how do we decide which little bits are going to be most important within the state, and how do I identify what it is we want to do? And so for a few years, developed some techniques of how to do this. And one of them is refining these maps of species distribution so we get a better idea of where they are in a particular locale. So instead of the big global maps that are kind of broad patterns, we need something more detailed. And so an example of that is this bird here, right? The super charismatic, greenish, grayish bird in the clouds. This is the gray-winged cotinga. It's actually endemic to Rio de Janeiro, so really one of the rarest birds in the world. And here we have the state of Rio de Janeiro again, right? So here's like the Christ statue that shows up in all the photos and videos here in the capital of the state. And you can see the central mountains here, right? Going through the state. And that's where most of the forest still is. And so we did some simple models of where the habitat of this species would be, and got these little blue blobs, you know, going across the mountain ranges. So National Geographic expedition, you know, got some people together to go out there and confirm that this bird is in a lot of these places. They're super hard to get to. Some of them had to get to by helicopter. It's like, well, you know, we can get a good idea of where individual species are, where their habitat is. Now, if you do that for a lot of species, you start to tease out some sort of fine scale patterns of priorities. Right? So here's the same area, a little bit different orientation. So down here in the bottom left, it's Rio de Janeiro again. Blue to red is the number of endangered birds predicted to occur. So you can see most areas are some color on that scale, right? The gray areas don't have any forest. If you look in the east part of the state, what comes out is this red spot here. This turns out to be the União Biological Reserve, Union Biological Reserve, which is a pretty well protected place. And, you know, if you think about this, we already said, you know, Rio de Janeiro has the highest concentration of endangered birds. And so this is the place within Rio that has the highest number of endangered birds. So that means this little bit here is like, you know, the most highest priority for bird conservation in the Americas. Right? So 2 continents, you know, that little fragment turns out to be probably the most important single place. And we can get a closer look at it here. So we've zoomed in on Google Earth. So this fragment here on the right is the biological reserve. It's not huge. It's about 3,000 hectares. But you know, it has a problem, right? There's other forest here on the left, right? This forest actually goes up higher into the mountain chains and connects to the other forest throughout Rio. But it turns out there's a little gap here. Right? You can kind of see here. We'll zoom in on it here in a second. So this super important forest fragment, turns out it's isolated. Right? And there's decades of research have shown that, you know, if you isolate habitats, principally this research has been done in forest fragments, but some in, you know, clearings in forest, including by people, you know, there at NC State and other US universities here in Brazil, that show that small fragments lose species. Right? And the smaller your fragment, the more species it will lose, and the faster it's going to lose them. So this fragment, 3,000 hectares, well, it's not so good. It'll hang on to its species for a while, but in the long run, it's pretty vulnerable to things going extinct. So, went there years ago. I started going there. Took some pictures here so I can have some a better view to explain this. So here is that gap. Right? So we've turned around the direction here. This is actually the biological reserve on the left-hand side now. The other forest on the right, going up into the mountains. And it's, it's not that big a gap, right? You can walk across this in, 15 minutes or so, 15, 20 minutes or so. It's got a few trees scattered on it. It's also got a little dirt road. You say, well, it's not too bad, but there are a lot of species just won't cross that gap. Right? There's a lot of species, forest interior species, we'll get to an edge like that, and they'll turn around and say, no, I'm not going to go across that gap. So it's a barrier. Well, we got together with a lot of other people, including people that work there, local NGO, thinking about this. Well, what can we do about this problem? Well, it turns out there was other people working here that, had come to a very similar sort of conclusion, but not for birds. They worked on this species. Right? Some of you might have seen this guy. All right, the golden line tamarin is used to be one of the world's most endangered primates. It turns out it does pretty well in zoos for captive breeding programs. So a lot of zoos will have these guys. So you might have come across them. It's kind of the symbol of the Atlantic forest now. It's even on the currency of Brazil. And there was a local group, the Golden Lion Tamarin Association, was working for the conservation of the species, partnering with them, and said, well, what can we do to reconnect this forest fragment? It's so important for birds, it's important for this mammal, it's important for a lot of other species. And so at this point, you kind of slide out of the world of science and biology and say, well, what are some practical solutions here? What do we got to do? And part of it was going to see, who owns this land, who manages it, who are we going to have to deal with, and what are the solutions. So one of the things we say, obviously, is like, well, we want to have a corridor. We want to reconnect that forest. So let's go talk to the person who owns it and see if they would be willing to, make some deal and try and restore some of that area. That turns out that this guy here in the middle, talked with him for years, right? This is the reserve manager there, that biological reserve. These people around work for the Golden Line Tamarin Association. Long story short, many years of arguing and negotiating. It turns out this guy really doesn't care, doesn't like conservation, doesn't care about tamarins. His dogs ate some of the tamarins. He set fire to the biological reserves. Okay, guys is difficult to deal with. So it turns out the only thing he was interested in was money. So we had to buy the farm. So we created an NGO to raise money. And after a few years, we bought that farm. It became known as Fazenda Dourada, the Golden Farm afterwards. So we bought it and we started reforesting it. So here with the local community, this is the Biological Reserve Director again, working with the local municipalities, local school kids, bring them in, teach them about the reserve. Why is it so important? What do we do to protect it? And they plant some trees. They accompany these trees over the years to, see how they're doing. And you can see this all now. Back to our Google Earth image. Right? This one we saw earlier is from 2007, but this is before we bought this fazenda, which is right around here. If you look at it today, that area is reconnected. Right? Successfully rebuilt connectivity in this landscape, working with the people. And that means, all these species in this super high priority forest fragment can now eventually pass over to the other forests and up into the higher mountains. Right? And that's super important because we know a lot of these things are seasonal migrants. They're very likely to need to spread out as climate changes. We're not really sure where they're going to need to move to. You can see here, there were a lot of people involved. These are some of my colleagues at the time, and the corridors here in the background. Right? This is a few years ago. The trees are just now getting started. Looks like it's much higher than this now. It's about, 5-10 meters tall at this point, so it's going to be a pretty good forest. And we have actually documented things use it. Golden line tamarins have been seen, the whole family units moving across this corridor. They have dispersed from that reserve to the other forests, so we can, we can all pat ourselves on the back, say, hey, we actually did reconnect a place. Success for conservation. And about a year ago, because of those efforts, we were also, well, I won't take credit for any of this. I wasn't involved in this. It was, mostly Golden Line Tamarin Association and the Biological Reserve Director fought for expanding the reserve. Right, so this yellow area is the original biological reserve. They fought to expand it to this green outlined area, which included the corridor and expanded into that other forest to the west. And part of the argument they were able to make is like, hey, we've now reconnected this landscape. It makes sense to reconnect, to expand this reserve to this other forest because the species we know are moving between these areas. So it's really important for the success of the reserve. They'll be bigger and have a better chance of long-term survival. So there's also some other efforts underway. I won't go into detail because I don't have a whole lot of time here, but the next corridor in this same landscape, it's a little further west, but it's to reconnect another biological reserve. But that one is separated by a much more difficult barrier. Right? As you can see in the background here, there's some forest off in the distance. That's the Poço de Santos Biological Reserve. If you imagine back on this side over here, there's other forest going up the mountains. And in between, there's this 4-lane highway. It's one of the main highways of Brazil, the BR-101. And after many years of battling, we successfully won a legal battle that the company that managed that highway has to build a forested bridge going across that highway. It's part of the deal for them to charge tolls and make lots of money off this road. So what you're seeing here is the pictures of a few months ago of that bridge being constructed from one side of the highway to the other, and then early next year it will be planted with seedlings, and it will be the first forested and the first corridor bridge in all of Brazil, which they resisted fiercely and said, you can't do it, it's not going to work in Brazil. We showed them it had been done in other countries, in Canada, and the US, and Singapore, Netherlands. So if you ever come to Rio de Janeiro, next year or in a few years, be sure to see this bridge because they should have some trees on it by then. It's only about an hour and a half outside of Rio de Janeiro City. So what does this mean for other places, particularly the US? I still do some work in the US. I assume many of you are working on projects in the US as well. If we look at the US's situation for protected areas, these, this map shows all of in green, darker greens, all of the more strictly protected areas. And then a blue, sort of the federal lands and a few other categories for state public lands. And then the rest is basically private land. It's very fragmented. So all these dark green areas, they tend to be little bits. They're isolated from the rest of the landscape. It turns out that even though we've protected a fair amount of area, it doesn't do it very well in the sense of where places have been located and how well they're connected to one another. So there's some people who have been looking at this to try and identify where the opportunities for reestablishing connectivity in the US amongst protected areas. And a lot of this is motivated by climate change, right? Knowing that species are going to need to move in the future. They're going to have some way of getting from one place to another, maybe one protected area to another, or through private lands. And so there's some work, a lot of it led by a colleague of mine, Travis Belot, who's at the Wilderness Society, creating maps like this, where in this case, blue is areas that have a higher potential value for corridors among protected areas. You can see in the center part of the country, it's quite difficult. So we've converted most things, and there's not many protected areas to connect. The south and southeast is also quite difficult, but there are some promising areas here in blue. If you combine a map like that with biodiversity, sort of a more species-specific look, you get some other interesting patterns. This is some work I led about 5 years ago to try and identify the areas that were really important in the US for complementing the existing protected areas. And so all these different colors are areas that are higher priority for species. This was all the terrestrial vertebrates, fish, and trees went into this analysis. So it's the areas that tend to be the species that have been left out, right? Or the things that are really vulnerable or easy to go extinct. I can say the southeast shows up as really super important, right? Western North Carolina is a super high peak, Eastern Tennessee. There's a lot of salamanders and fish there, but also, you know, California, the Northwest, parts of Texas have some really high priority areas. Right? I actually started out in conservation right here, right in East Tennessee. That's where I grew up, chasing salamanders and not realizing that you shouldn't use salamanders for fish bait because some of them are endangered species, but I didn't learn that until I went to graduate school. Right? So if you combine a map like that with maps of connectivity, like Travis has been working on, you can start to get an idea of which parts of the US may be really high priority for new protections or increasing connectivity, where we could focus our efforts to have the best impact for keeping biodiversity into the future. And I'm not going to interpret this map. It's sort of just a synthesis of those other things where the redder areas are sort of a higher priority based on a few metrics that Travis put together. So just thinking about the future, where to go with this sort of research and practice, you know, in the US or anywhere. I think maybe Krishna will you know, have a focus more on US, some more detailed look. You know, there's some things we could really look at that would really help in planning. One of those is, you might call a climate corridor. We don't really know really well where species will need to move in the future, considering the climate's changing. How are they going to need to respond to that? Where might be the best areas that we kind of protect a corridor that they can disperse on their own through, and how much that varies between species. Rivers and the connectivity of rivers is something that doesn't get nearly enough attention. I think most of these maps I showed were, you know, terrestrial biodiversity, but rivers and, you know, how are they going to change in the future and how we need to maintain their biodiversity is something that probably doesn't get enough attention. And there's an element of communication of these sort of issues to the public, especially where biodiversity is and which parts of it are really at risk. I mean, if you ask, you know, most people, you know, what do they know about Brazil? They'll say the Amazon. Right? I don't know how many people I've run into. And it's like, well, I live, you know, sometimes in Rio de Janeiro, sometimes São Paulo, and they assume I live in the Amazon. It's like, no, it's not the Amazon. But all the endangered species are in this other forest you probably never heard of. So, you know, saving the Atlantic forest probably has a bigger impact than trying to save a piece of the Amazon. But, you know, we don't do such a great job so far at communicating that to the public. Even within Brazil, I have that difficulty. So I've done some of this effort with trying to get this out to a website called biodiversitymapping.org. So a lot of these maps you've seen are there, and so you could use them for whatever. Public use for, you know, lectures, other research, things like that. But I think a lot of people should, you know, try and invest some time in that, trying to get this information to the broader public and out of the academic community if possible. We don't get much training in that, but, you know, do what you can. Maybe, I don't know how much NC State nowadays is encouraging that. You know, there may already be some existing programs. So that's the quick version of what I've been working on. There's a lot of people involved in this. One goes through this list, a whole bunch of institutions, lots and lots of people funding. So yeah, that's my view of biodiversity and how the world is changing and what we can do to try and keep species around for the future.
Thank you. Thanks. So now we have Krishna for his presentation. How do I go back to? Okay. Sure. Okay.
Leo, thank you all for coming, and especially thanks to the Global Change Fellows for inviting me. And thanks for Clinton actually to providing a very different view of mapping biodiversity in a changing environment. So I'm actually going to talk a little bit more about how we actually do that. So my background is mainly sort of focusing on methodology and how we estimate things, how we evaluate change, and how we ultimately conserve biodiversity. So I was asked to talk about two specific case studies, so I'll get to those in the Southeast in just a little bit. But in general, when we're trying to map biodiversity, we have to think about land use, climate change, overexploitation, disease, habitat loss. All of these things are all pretty well versed in. But really what we need to do is think about how do we map and monitor these things as they change in the future. And not only do these individual elements actually change, obviously land use is changing through time and space. Climate change is changing over time and space as well, the effect of climate change. But really we are interested in the effect of all of these things and how species respond to these different effects. And of course that can change over time or space. And so when we think about mapping biodiversity, ultimately we want a distribution of species. We want some map that shows where species occur, what are they related to, or what are they correlated with in the environment. And so typically people use sort of species distribution models where they try to look at how these individual species or groups of species are responding to the environment, and then how they're going to respond in the future. We want a prediction of what that future response is going to be. So obviously, if you're thinking about global change, in climate, we want to know how are species going to respond to climate change, not only now, but in the future. And so I'm going to focus on two different sort of elements or things that I actually think are really important when we start trying to address these specific questions. One is, there's this huge amount of available data sources now that we can use to map species distribution and to understand the effect of these environmental variables. So how do we actually use these growing number of data sources? And then also, how do we account for change in the environmental response? Like I said before, the response, the effect of land use, the effect of climate, the effect of habitat loss varies over space and time. So the same way the species responds now, it may respond very differently 20 years or 50 years from now. So we need to be able to capture that sort of variation and effect in some specific manner. And so I'll talk about two different case studies. The first sort of deals with how we sort of handle growing numbers of data sources, and the second deals with how we account for change in the environmental response. So this first one, this was work that was a huge collaborative effort that started actually with a collaboration between Duke, NC State, and UNC at SAMC, which is a statistical and mathematical sort of collaborative that these three different universities are part of. And this was work that was published 2 years ago in Ecology. But so generally, we're talking about species distribution modeling, right? So we want to understand how species respond to different environmental variables across some geographic distribution. So we relate these observations of a species to the environmental characteristics. So for example, we might have field records or maps of the environment and the individual species. We have a statistical model that then gives us a probability of that species occurring in some specific location. And so ultimately, we usually want to do this over some large spatial extent. So you saw the examples that Clinton provided, mapping biodiversity across the entire world. That's a very big challenge. But even mapping biodiversity across, say, North Carolina is also a very big challenge with a very large spatial and temporal extent. So it makes it almost impossible to have dedicated, field teams, where we have a whole bunch of experts that have been trained in a very specific manner to go out and sample this large area. And in addition, the data requirements are just extraordinary. You need a ton of data to understand the distribution of a species across a very large space. And so what's happened is there's been this huge explosion of citizen science data. There's many different forums, there's tons of different apps that are now available. And so what this does is it's sort of this large potential for a lot of different data sources that you can use to map the species distribution. There's two advantages, and obviously the quantity of the data, the spatial and temporal coverage of the data as well. And then there's a cost advantage too, right? You don't have to pay anybody to do a very minimal amount of cost to have citizen scientists go out and collect data. So for example, this is actually the breeding bird survey, which is a national survey that covers the US. But it's sort of more or less a design survey that uses volunteers, but they're trained volunteers. And you can look at their effort here across the Southeast. And so again, there's very little effort in almost every place, but then there's certain areas that have a little bit more effort. But we can compare this to eBird, which is a citizen science project out of Cornell Lab of Ornithology. And so note first, this is the square root of effort. So if you go back to this scale, you're up to about 150 here. So this is, 40 squared, that's the amount of effort that we're talking about here. So not only notice that there's just a huge amount of effort, but also it's in different locations, right? You get, Atlanta, you get this sort of Northern Virginia, DC area, and so you get this large amount of effort in highly dense populated areas, which can be good. But you also get effort in areas that you just didn't get effort in before. So again, with BDS, there's really no effort in a lot of South Carolina, Georgia, Alabama, but you look here, and now there's a good bit all interspersed throughout here. So again, there's this huge advantage to using citizen science data, especially in the spatial coverage and the actual quantity of data that you can get. And this can be really helpful, again, for urban areas, which are sometimes overlooked, and especially for rare species. Lots of times, especially with birds, people go out and they're really looking for specific kinds of birds, and so they put a ton of effort in to sort of confirm that a specific species lives in a specific area. Obviously, there's a lot of challenges with using citizen science data. So observer variation, again, you may have a ton of variation in sort of the observer's ability to detect a species. Sampling effort, as we saw before, there's a lot more effort in these urban or more densely populated areas. And then measurement or recording areas. You could hypothesize that some of the citizen scientists are don't do as good of a job collecting data or identifying or detecting individual species. And obviously these sort of observer variation and measurement recording areas are two areas that have probably been almost eliminated for a lot of different reasons for a lot of these different citizen science projects. A lot of stuff is moving towards camera traps or a photographic image of a species, so it can be sort of vetted by an expert. But either way, those are sort of the main challenges with a lot of citizen science data. So the question is then, how do we best use this citizen science data? Debate about the best way to analyze such data, but ultimately, you're trying to share information across space and across these different data sources. So maybe you have some design survey that has a fair amount of effort, but maybe in a smaller area. And then you have another sort of citizen science database that has a lot more spatial extent and covers a lot more area. So how do you combine those two sources of information? So what we did is develop a continuum of approaches. We evaluated which approach was most useful. A case study for the brown-headed Nuthatch. It's just a very few number of results just so we can kind of move on. But I want to talk a little bit about how we do this. And this might be a review to some people or something they've already seen, but I kind of feel like it helps you sort of think about what you're trying to do. So our objective is to map the geographic range of a species. So we have observations of a species in different locations. We want to know, where is the species actually occurring? Can we get a probability of species occurrence based on this information? And so we also have to account for all these different sources of variation and bias, right? There's sampling effort, there's detection bias, there's variation in observability, and so many other things that we have to account for. So what we use is a hierarchical model to do this. And the reason we use a hierarchical model is because it allows us to separate out this ecological process, which is what we care about, the true sort of underlying occurrence probability of a species or species. But we can separate that out from this observation process. Right? The observation process is the data that we actually observe, and it's sort of wrought with all these problems, these sources of variation and bias. So in a hierarchical model, we can separate these out so we can focus on the ecological process, the species occurrence, and then separate that from the data and the observation process. So for example, we can then have all these things that are affecting the ecological process. We think that land use or climate change or other environmental covariates are actually influencing where species are occurring and how they're responding to these different things. So now we can have a model that separates out this piece from this piece, where we have false negatives, false positives, variable effort, and all these things are just affecting the data that you actually observe, but not necessarily affecting the true underlying species occurrence or ecological process. So we use a hierarchical model to do that. And again, for the brown-headed nuthatch, we had two different data sources. We had the breeding bird survey, which I said before is a nationwide survey. The routes are 25 miles each. They stop every half mile and do a 3-minute point count. So for 3 minutes, they record all the bird species they can hear or see. And this is roughly, sort of relies on trained observers for the most part. So we use data from 2012, and then we combine that with eBird, which is a citizen science database, which is probably well over 300 million records by now. But it's essentially a checklist of individual birds, and they include this auxiliary information like effort, so how long people were out looking for birds. And we use the count data from this for 2012. I'm not going to go into too much details about the actual model. The underlying sort of hierarchical model that we had was what's called a multivariate conditional autoregressive model, which sounds lovely. But the whole idea is that we're trying to share information among these different data sets and across space. So we can think about the first data set being the BDS data, where we can estimate occupancy probability and the detection probability. So basically, if a species is there, what's the probability that we're going to actually detect it? And then for data set 2, it's count model, so it's a different kind of data that we're actually getting. It's counts, so that gives us some idea about the local intensity of that individual species in a specific area. So we looked at 4 different models. We had a single data set model, which was BBS data only. We had a shared parameters model, which was called joint likelihood, but basically the idea is that we're saying, hey, we have BBS data and we have eBird data. They're both equally good, and so we're going to treat them as sort of equal weights and put them in the same model. Then we had a correlated parameters model. Well, here we're sharing information indirectly. It's really just coming from the cross covariance of the multivariate CAR model. But again, the idea is that you're sharing some information, but you may not believe that both data sets are equal. So it's not a direct sharing of information, it's sort of indirect, which allows for one of the data sets maybe not being as good as the other one. And then we had a simple covariate model where basically we take the eBird data and we turn it into just a site level covariate. So we take some summary at some particular location, maybe the total number of counts, or the counts per unit effort, and we use that as a covariate influencing occupancy in the BBS data. So visually, you can kind of think of this, and again, there's a lot going on here, but what you can focus on is just in the joint likelihood, you have data set 1, data set 2, and they're both equally informing about the species distribution, this unobserved state that we care about. In the correlation model, you have data set 1 here and data set 2, and so the sort of correlation between the process that's going on here, or is correlated with the process that's going on here. That's why it's called the correlated model. So again, the information isn't shared directly. It's not informing the exact same parameter. And in the covariate model, you take the eBird data, you take some summary of it, and that's used to inform your ecological process for the BBS data. So what did we find? We found that all the models that incorporated eBird had a smaller mean squared error relative to the BBS only model. We found that the BBS model predicted sort of higher occurrence beyond the boundary of the species. So if you look at sort of a range map and some other information about where that species occurs, you normally see this kind of dip right here where it doesn't really occur very much. And you can see the BBS only data set doesn't really pick that up. It kind of has a sort of higher level of occupancy all in this area that isn't really a part of their range. And so again, the idea is that using that eBird data in some rigorous manner with these sort of models that we developed allows you to better estimate the predictive, the distribution of brown-headed nuthatch. And so even the covariate model, the simple covariate model, outperformed the BBS only model as well. So again, this was sort of a framework for how we can think about taking 2, 3, 4, 5 different data sets and combine that information together to get a better estimate of sort of that geographic distribution or geographic range. So now I'm going to switch gears not too much. We go back to species distribution modeling. So remember what the first objective was, we were talking about how we combine data sets. And the second one is how do we look at variable effects of our response to individual covariates. And so just to go back to what a species distribution model is, you have these field records and maps of the environment, you have a statistical model, and you're interested in that probability of the species is present. So you can kind of formalize this in a very simple way. Well, first off, so most of these SDMs rely on some form of regression, some linear model or regression is how all of this is sort of done. So all those maps people use is usually based on this sort of approach. And so here we can say, what if we have some response? Maybe it's bobcat occurrences. So this is detection, non-detection data across the whole country. We'll actually look just at North Carolina. But again, this is so people have gone out in some survey and said, it's here or it's not here, and you collect that information. That forms your response. You then maybe have some covariate that you're interested in. So what is the effect of housing density on the presence or distribution of bobcats? So you have this covariate, and then you have these parameters. You have an intercept and a slope that you have to estimate. So maybe you estimate those from the data, ends up being 0.2 and 0.5, something like that. But the whole point behind this is that this value here, well, really both of these values, are fixed. So no matter where you go, the effect of housing density is exactly the same on bobcat occurrence. So is that a sort of good assumption? Maybe, maybe not. But most likely, this effect probably varies by space and by time. So maybe the effect of housing density 20 years ago is different than the effect of housing density 20 years into the future. And so how do we sort of handle that kind of information, or how do we account for that variable effect of a covariate? And so what we call that is non-stationarity. There's variation in the direction and or magnitude of an effect across space or time. And so across space, again, this is just a hypothetical here. Say we're interested in the effect of forest cover on deer abundance or deer distribution in North Carolina. So we have all these camera traps across the state. We then have a distribution of forest cover. So maybe this is a GIS layer or some other environmental layer that we can get. And so now, like we showed before, maybe the effect of forest cover is constant. It's fixed across the entire state. So wherever you see forest cover, there's a higher probability that you're going to see deer. So maybe it's 0.5 or 1 or 2 or something like that. But it's fixed. It doesn't change depending on where you are in the state. But maybe there's some sort of like coarse scale variation that you need to account for. So we have these different ecoregions in the state. We have mountains, we have the Piedmont and coastal plains. So maybe the effect of forest cover is different in the mountains than it is in the coastal plain. And so we could account for that with this sort of coarse scale model. And then finally, the last sort of level would be this fine scale variation in the effect of forest cover. And so maybe we have, there's sort of a localized effect depending where you are in the state. And so we're going to develop a model that sort of evaluates this approach with this approach with this approach. And again, just to touch on stationary, it can also be over time. So we're kind of focusing on spatial variation right now, but it could also be temporal, which makes a lot more sense for global change. But again, you have the idea that if something is stationary, maybe there's some mean and there's sort of yearly fluctuations around, say it's the total abundance, like average abundance of deer in the state. And so it kind of bounces around, but it's relatively stable. That mean is not changing over a long period of time, so it's considered stationary. But in reality, what if it starts to change? What if that mean switches? So instead of being around whatever this is, it's now averaging sort of around this with its local variation, or annual variation. And so this whole idea is that it's non-stationary. So the effect of something might change over time. And that's probably making the most sense with climate change. I mean, obviously, when you talk about climate change, people say that it is non-stationary, right? There's a non-linear effect of climate change as we move forward in time. The effect of climate change, say 100 years ago, is not the same as the effect of climate change now. And they're sort of predicted that's going to continue to change in the future. So this sort of sets up a framework for how we can think about spatial variation and our spatial non-stationarity as well as temporal non-stationarity. So getting back to my example, so our question here is, does accounting for non-stationarity improve our ability to estimate a species distribution range or geographic range? And then can we detect non-stationarity in the response of the mammal community to environmental covariates in North Carolina? So that's the sort of case study we're going to look at. And again, I'm kind of going through this quickly, just sort of kind of give you an overview of what's going on. But the data comes from, this is actually a project that Roland Kays at the museum has started. So it was called Cannon Critters, and then sort of in conjunction with this whole project with eMammal, there's basically about 3,260 camera points across the state from 2012 to 2018, and about 65,000 camera days. And so you can see all the little dots are cameras. The red dots represent sort of main cities, I think with a population of over 90,000. But there's a fair amount of fair good coverage across the entire state with these camera traps. So again, our approach here, we're interested in occupancy or occurrence probability to make a map of species distribution. We're going to focus on the bobcat here in North Carolina. And we have 4 different models. We have a traditional regression model with just a fixed effect. We then have a model with a spatial random effect. And then we add to that these sort of non-stationarity models, this eco-region where we look at the different regions having different effects. And then a fine scale one where basically, there's a localized effect of a specific covariate. We had a whole range of covariates here. These were spatially varying. We had landscape composition, landscape configuration, and then we had site level information as well. I'm not going to spend too much time on this. I'm not going to spend too much time on this, but the approach we use is what's called a spatially varying coefficients model. And then the way that we did inference was an integrated nested place approximation, or INLA, which is just an alternative to doing NC for Bayesian models. Again, that's not super necessary to understand at this point. And then we sort of evaluated model fit in a couple of different ways with WIC and then predictive performance using the AUC. And so the main results for this were that the spatially varying coefficient model had the best fit in predictive performance. We also had great improvement just by incorporating the spatial random effect, so allowing for any kind of spatial correlation and sort of picking up that additional spatial correlation using the spatial random effect outperformed using that fixed effect regardless. And then the eco-region model had marginal improvement over the spatial random effect model. So we really saw a big jump from the fixed effect to a spatial random effects model, and then a big jump from the spatial random effects model and the eco-region model to that fine level variation model. And this is work that our PhD student Brent Pease is working on. And so again, you can start thinking about estimated occurrence. And so, these are the different models. This is the fine scale non-stationarity model that performed the best. And so what's the point of this, right? So now we can estimate the distribution of a species and what it's responding to and how that varies across space better than we could have before. And so now you can start thinking about, well, what if we started to stack these individual species distribution models on top of each other and looked at species richness for like, in this case, the mammal community. And so you can start to see that these pockets across the state that actually have a much higher level of species richness than some of the other ones. And so we focused on the methods here, but again, the idea, the ultimate goal is to do a better job mapping distribution of species and conserving biodiversity and understanding how species and groups of species respond to the environment and how that's changing to time. So again, integrating multiple sources of data can be better. We have to be careful that not all data sources are equal. So you have to really make sure that you sort of vetted the data sources and you have a realistic and rigorous way to combine those data sources by accounting for or recognizing different sources of bias and error. One of the big problems with combining data sources is the spatial and temporal mismatch of the data sources. Maybe you have one data set that's at this level, then you have another data set that's at a much finer level. So it could be county records versus individual site level information, or it's records that were collected from 1970 to 1990, and then you have an updated survey from 2015 to 2018. So how do you reconcile those differences in the spatial extent and the temporal extent as well? And then we found that accounting for spatial non-stationarity provides more robust estimates of environmental relationships, provides more accurate maps of species distribution, which is ultimately what we're trying to do here. And then the spatially varying coefficient model really revealed the variable scale at which species are responding. So sometimes they may be responding at a much finer scale, or in different places, they might be responding at a larger scale. So maybe in the mountains, they're responding to forest cover at a very small scale, but on the coast, they're responding at a very large scale. And so we were able to sort of detect those variations in the scale of response, which has a lot of implications for conservation, understanding how to manage these species. And ultimately, we sort of provide in some way a framework for thinking about how climate change, the effect of climate change, varies across space and time, and how we can account for that. And real quickly, just talk about some of our future work. So we have a paper in Ecology that just came out on this spatial and temporal mismatch for these integrated species distribution models. Brent's been working on combining data sources and accounting for the non-stationarity. And then a lot of this is being used in a larger project for conservation design. We're interested in evaluating the interventions and actions to conserve biodiversity, and then optimize over a set of actions and outcomes to maximize biodiversity. So I know I went through that very quickly, but.
I know it is already 4:30, but if anybody wants to stay for questions, we will have some time for that. Clayton, can you hear us?
Yes, I hear you. Krishna, I am jealous of how much data you have.
I don't know about that. You can think for the state data.
Let me make a quick comment. I think it was a nice compliment, Krishna's presentation, because it sort of presents the other side of, I know there's always data limitations, but you have quite a bit of data. You can explore these nice models of species distributions. And those are the sort of things we really need if we want to make good plans for biodiversity, have a better sense of where things are. And it's a challenge. It's getting easier. Kind of the other extreme was, well, in parts of the Atlantic forest is actually pretty good for Brazil, but it was part of a process for planting the Atlantic forest. And if you looked at like the amphibians, there's about 600 species of amphibians in the Atlantic forest, and about 50 of those have no data points, and another 50 or 75 had one, like basically the type locality. And it's this challenge of like, oh, we have to make decisions based on data that aren't very good or almost absent, when what we would like to have is, a good map of where the habitat is, where the species is, like, some of the stuff that Krishna had. But most of the time we're somewhere in between. We have data, it's getting better. We have some citizen science data with the challenges it has. And I think we face this difficulty of, how do we get comfortable, we in the grand scheme of, we never have all the data we want in the best format, but somebody has to make some decisions based on whatever we know. And that's a tough one because it always leaves some people unhappy. So yeah, I guess whatever your situation, wherever you're working, you're going to face a data limitation, but do the best you can. And somebody out there is probably waiting for whatever you can produce to try and help them make decisions.
Thank you. So anybody have questions for any of the speakers? Yep.
For citizen science, can you request that they look for certain species, or I guess I don't know that much about how it works?
Yeah, so it's getting there. So there's a lot of Cornell ornithology has kind of been at the forefront of a lot of this, where they've sort of incentivized certain locations and certain species to try to find. I think they had an app that was sort of like a game where you got points for the more species and things that you were able to observe. We tried that earlier on, kind of sending out messages to sort of listservs and things, telling people that we were really interested in trying to find this species. And depending on the species and the group and everything, you got sort of variable responses. But I would think, from what I've heard, there's a lot of it trying to sort of fall into, I don't know, a game, basically. I don't know how else to describe that, but so there's really just incentivizing this kind of research.
Any other questions? Yep.
So this is about the non-stationarity. I can wrap my brain around how we might find that in a spatial sense. But do you think there's prospects for there being data to look for that kind of changing relationship over time?
Yeah, I think
That
so.
hasn't been shown.
Yeah, it has. I mean, it depends on the scale, right? Because there's things that are sampled. Ecology is a little bit more difficult, but things that are sampled like on a weekly basis, and so then you could look at, you have 52 weeks, in a single year. If you have 3 years worth of data, that's a lot of different data points that you could then use. It's the same idea where you just have a space, like you basically let that effect of time vary, so that you could have an individual, like a different effect at every single time point. And so I'm trying to think if I've seen it in ecology. I would think, I think there's some version of it with a lot of the time series stuff, where people have had time series for a really long period of time, and they let different effects sort of vary by time. But yeah, I think it's the same idea. I mean, we're sort of continuing to grow our data sources, so I think it's pretty possible.
I have a question for Clinton. Hey, Clinton, what are the prospects for increased biodiversity collection in Brazil? How is that going in the country? Which routes, which sort of strategies are working, which are not?
Yeah, it's a good question. It's variable. I mean, if you look at the last couple of years, science has basically been gutted in Brazil because the economic crisis and stuff. So there's not a huge amount coming from the main academic community as much because of the lack of resources, especially in more remote areas. There's been some efforts with citizen science. It's struggling. Like some people use eBird, some people use a thing called Wikibird, basically. But the data they're not as precise. iNaturalist has struggled in Brazil, just not gotten wide uptake yet. I've been trying to work with some people on that, but it's not taken off. Part of it is there's not, within Brazil, there's not as much of this culture of, going out into nature just to look for things. Part of that's a security issue. It's not safe for many areas. Aside from the biodiversity that highly venomous snakes, there's like bandits. So you can't just go wandering off. I think it has a lot more prospect than expecting, the academic community and the museum community to build a big enough data set to do a lot of these things. There's just simply not enough people qualified. They're going to have the time to do it. We're going to have to enroll this broader society and, getting out there and snapping some pictures. Camera traps, I don't know, camera traps get stolen, so somebody has to take care of them. But there's definitely a need for it, especially, as I said, there's a lot of species where there's just nothing known, or at least available data. I mean, I've had plenty of things of iNaturalist that, I've just snapped a picture and somebody will identify it. I don't know what it is, even years later, and it'll be one of the only records in like 500 miles of that species. So yeah, it is welcome. And yeah, if you have ideas on how to go about it, what strategies have worked in the places you work that have really helped improve the uptake, I'm all ears.
Any other questions or? Okay.
Krishna, thanks. I also had a question on the non-stationary component. It was the intent, I mean, I think I understand the mechanism that you're using, but is the intent in this case to fit models with data that include and exclude stationary or non-stationary processes, so the data can inform you whether those are happening, or are you actually in this case using the data to try to estimate something about the rate change of a non-stationary process? That was part of this fight.
Sorry. So the first thing you said is correct. So we're letting the data sort of inform, is there non-stationarity sort of happening, and at what scale is it happening? We have the rate of the non-stationarity. That would be interesting. I mean, that would be sort of a more temporal component to it, which you could probably do without.
I've not seen that, I don't think, in papers where they're actually trying to use the data to estimate that component of the system as sort of a direct objective of the model. Do you think that it would actually work?
Yeah, I mean, I think in statistics it happens. So like a dynamic linear model is essentially that, where you have some temporal component, and then maybe you have something that you're interested in. So in this case, you could have sort of the scale of the effect, and you want to see if that changes over time. So maybe it's a really localized effect, like we found the sort of fine scale model works best, but maybe, you know, as you go through time, that scale effect will change. But yeah, it would require a lot of data to do, but that would be pretty interesting. Go for it.
No.
Okay, so thank you everybody. Thanks for the speakers for these talks, and we'll see you in the next Global Change seminar.